Good morning to all of you. Myself, Professor NVRK from SND College of Engineering and Research Center, Yeola, working as a assistant professor in Electrical Engineering Department. So today we will discuss the new topic of course, electrical measurement and instrumentation. The topic name is displacement measurement. Displacement measurement by using LVDT and RVDT. The methods which is used to measure the displacement, that is LVDT and RVDT. Now today we will discuss in that lecture. In that lecture we will discuss the displacement measurement by using LVDT. What is the LVDT? It is a linear variable differential transformer. It is an electromechanical type inductive transducer that converts rectilinear displacement into the AC electrical signal. AC electrical signal. So LVDT is a secondary transducer. Hence, physical quantities such as force, weight, tension, pressure, etc. are first converted into the displacement by a primary transducer, and then LVDT is used to measure it in terms of corresponding electrical signal. Means the LVDT which will use according to their name, linear variable differential transformer, they will use for measurement of linear displacement by using differential transformer. Means in that the transformer having two secondary winding and the difference between that two winding, it is your output voltage. The construction of LVDT consists of one primary winding P and two secondary windings S1 and S2 mounted on a cylindrical former. Both the secondary windings have S1 and S2 have an equal number of turns. In that secondary winding are divided into the two equal number of turns and is placed identically on either side of primary winding in such a way that the net output voltage, the net output of the secondary winding is the difference between the difference of the voltage of both secondary windings. Means the output of the voltage of secondary winding is the difference between the two voltages, that is of secondary first coil and secondary second coil. Then the output voltage is Vs1 minus V secondary minus V secondary 1 minus V secondary 2. The hydrogen annealing is done on the iron core to reduce harmonics residual voltage of the core and turns and thus provides high sensitivity. The movable core is also is laminated in order to reduce the eddy current losses. To reduce the eddy current loss, the core should be laminated. The displacement to be measured is attached to this movable soft iron core. The LVDT is placed inside the stainless steel housing because it will provide electrostatic and electromagnetic shielding. The working principle of LVDT is based on the mutual induction principle like transformer. When AC excitation of 5 to 15 volt at a frequency of 50 to 400 Hz is applied to primary winding, then a magnetic field is produced. This magnetic field induces a second, means when the supply is given to the primary winding, due to this mutual induction, the EMF is induced in the secondary winding, but the secondary winding is divided into two parts. Therefore, according to the mutual induction, the secondary having produces the two voltage, that is of secondary, the EMF across the first secondary winding is E1 and EMF across the second secondary winding is E2. Then the output is the difference between that two. That is E output is equal to E1 minus E2. E1 minus U2. E2. Now, according to the position of core, there are three cases that arises. So let's discuss this. The first condition is when core move towards S1. When core move towards S1, this is in that direction, S1. Then when the core of LVDT move towards secondary winding S1, then in that case, the EMF induced in the secondary winding, EMF induced in the or the flux linkage to the secondary winding, first secondary winding, that is S1, is greater than the S2. Then due to this flux linkage, the EMF induced in the first secondary winding, that is S1, is greater than the EMF induced in the S2. Therefore, E1 is greater than E2. Then the differential output voltage, that is E0 is equal to E output is equal to E1 minus E2. It will be positive. This means the output voltage of E0 will be in phase with the primary voltage. In second case, if the core move towards the S2, then according to that, the flux linkage with the S2 winding is greater than the S1 winding. Then according to the Faraday's law, the EMF induced in the winding S2 is greater than the EMF induced in the winding E1. Then the output voltage E1 minus E2, it is negative. Means this means that the output voltage will be in phase opposition, that is 180 degree with the primary voltage. And third position is when the core is at null position, then due to that the flux linkage of the both the secondary winding, that is S1 and S2 are same, and due to this the EMF induced in the both the secondary windings are same, E1 is equal to E2, then the net output voltage is 0. This is your displacement. This is the condition of the core moving, as the core is moving, means, and according to that output voltage, we can measure the displacement. Of the core. From all these three cases, we can have the following conclusions. That is, the direction of movement of an object can be identified with the help of differential output voltage of LVDT. That is, suppose output voltage E0 is positive, then this means that an object is moving towards the left from the null position. Similarly, if the output is negative, then it means that object is moved towards the right of the null position. Means if the voltage is positive, means object move towards move towards the left from the null position, and if the output is negative, then it means that the object is moved towards the right of the null position. The amount of magnitude of displacement is proportional to the differential output of LVDT. Means the more the output voltage, then it may be say that the more is the displacement of the object. If we take the core output of the former, then the net differential output of LVDT will be 0. Means at null position, the output of the LVDT is 0. In fact, corresponding to both the cases, whether core is moving either left or right to the null position, then the output voltage will be increased linearly up to 5 mm, 5 millimeter from null position, and after 5 millimeter output 0 will be non-linear. This is your graph showing the voltage. This is your displacement. As the displacement increases, the output voltage will be increases up to linear, and after that non-linear output will be taken. This is again negative side. This is negative side. The advantages of LVDT. The first advantage is smooth and wide range of operation. It has a very wide range of measurement of displacement. It can measure displacement ranging from 1.25 mm to 250 mm. It have high sensitivity. It is the sensitivity of LVDT is 40 volt per mm. Low hysteresis loss. LVDT gives the low hysteresis losses, hence the repeatability is excellent under all the conditions. No frictional losses, as the core moves in the hollow former, so there is no concept of friction losses, hence the output is accurate. Rugged operation. It can tolerate a high degree of shock and vibration, especially when the core is located with spring. Low power consumption. The LVDT consumes very low power, that is approximately 1 watt during its operation. Direct conversion to electrical signal. The linear displacement which will be directly converted into corresponding electrical voltage signal. The last one is high dynamic response. Due to the absence of the friction and dynamic friction losses, its dynamic response becomes very fast to change in the core position. Next, disadvantages. There are two disadvantages. Since LVDT is inductive transducer, so it is sensitive to stray magnetic field. Hence, an extra setup is required to protect it from stray magnetic field. Since it is an electromagnetic device, so it gets affected by the vibrations and temperature variation. The application of that, it is used to measure the physical quantities such as force, tension, pressure, weight, etc. This quantity first converted into displacement by the use of primary transducer. Then it is used to convert the displacement to the electrical signal. It mostly used in industries as well as servo mechanism. The industrial applications is automation, aircraft, turbine, satellite, and hydraulics, etc. The specifications of LVDT is the measurable range is plus 0.25 mm to plus minus 750. Operating frequency is 50 hertz to 20 kilohertz, and operating temperature is minus 265 to 600 degree Celsius. So in that lecture, we will we discussed the we dis, already discussed the topic, that is LVDT. In next lecture, we will study see the RVDT, which is used to measure the rotational motion or rotational displacement or angular displacement. How to measure it? They will be seen next lecture. So thank you.